I welcome you all to this platform. So I would like us to wait for others. So we are starting, don't forget, we are opening the group by 7:50 and we are going to wait for 10 minutes now. So by 8 o'clock on dot, we are going to start our lecture. So kindly wait for the time. Thank you. So I'd like to invite our tutor for today, Brother Olaoluwa Ogungbemi. Thank you. A round of applause for him as he's coming. Thank you so much.
Thank you very, very much for joining us today. We really appreciate you joining in with us. Let me set the camera well. Okay. So I believe everyone should be able to see me clearly now. So for today, we are going to be having a class on vector algebra. Vector algebra. And my aim in this class is to make sure you understand what vector is all about, for you to be able to tackle any problem that can come in the form of vector. So first, I would like to begin by explaining what vector is in itself. So what is vector? Well, if they ask what is vector, the definition we'll give immediately is that a vector is a quantity having both magnitude and direction. Vector is a quantity that has both magnitude and direction. But what does that actually really mean? Let's think about it. What is quantity in itself? Quantity is the measurement of something. When you gather something and you want to gauge it, that is quantity. So when we are talking about quantity that has a direction to it, that the detail about the direction is given, then we are talking about vector quantity. In the case of scalar quantity, then details about the direction is not given. Let me explain what I'm talking about to you. Let's say, for example, we are told that Adams moves from a point A, and we are told that he moves 3 meters. Adams A is at this point, and we are told he moved 3 meters. Now, moving, going to somewhere, that is a quantity, right? Yes, it is a quantity. Distance, length, yes. But in this case, they never told us in what direction Adams went. So it could have been in any direction. So, say, Adams could have gone 3 meters this way and ended up here. He could have gone 3 meters this way. He could have gone 3 meters this way. He could have gone 3 meters this way. Apologies for that. He could have gone 3 meters in any direction, so he could have ended up anywhere. But now, if they say Adams went 3 meters in the eastward direction, now, we know that if Adams was here, this is the position of Adams, and he starts moving. Eastward is what direction? Is to the right direction, and he moves 3 meters. So we know that Adams ended up where? We know that he ended up at this point because a direction was given. So that is the difference between scalar quantity and vector quantity. The fact that the direction in which that measurement is done is mentioned. So let's call this final point Adam gets to point B. So I hope you are able to understand the difference between scalar quantity and vector quantity now. So what else do we need to know about vector quantity? Yes, we need to know how we can represent it. Vector is usually represented, vector quantities are represented in capital letter or in small letter with an arrow on it. So it's going to be like this. Let's say in the case of Adams now here that we are talking about, we want to represent this vector, then we are going to say, either write it as a capital A, or if we are using a small a, then we have to indicate that there is a direction to it by putting an arrow on top of it. Also, we should also note that in vector, when you want to represent vector, the length or the magnitude, when we say magnitude, we mean the quantity of what we are talking about. Yes, so the magnitude of whatever we are measuring is represented in form of the line. So in case we are talking about length, or no, maybe not even length, maybe we are talking about force. Even if it is force, let's say we have a force of 10 Newton and a force of 20 Newton. So if we are representing it, we have to represent this force of 10 Newton to be half of the length of the line of this force of 20 Newton. So in this case, for this one, if this one is to be A, then we have a length from here to here and is 10 Newton. Then if we want to represent this other one, then it will have to be 20 Newton. So it will have to be double of this one. So the length represents the magnitude, and that arrow is very important. You put this arrow to indicate that there's a direction to it. So now that we understand what vector is, let's look at vector algebra and some operations relating to vector. To help us understand this, I would first want to give us examples of some vectors. I'll draw some vectors on the board here, then we can see how we can relate some conditions to it. So let's call this vector A, and we give it this direction, and we say it is 3 meters. We give a vector B, and we say it is in this direction, and we call it 4 meters. We have a vector C, we have 4 meters. Let's have our D on this side. Four meters. E. We have 3 meters, and F. 3 meters. Now let's look at this sets of vector representations here, and look at our first term we want to look at. Now we want to look at it. When is a vector equal? a vector can be said to be equal vectors when the magnitude and the direction, those two things, magnitude and direction, when they are both the same. What are we talking about? On this chart here now, which two representations can we see is in the same direction and is having the same magnitude? That would definitely be A and E. So we can say from here that vector A is equal to vector E. Okay? So I believe we are able to get that because they are in the same direction and they have the same magnitude. Also, we have negative vector. What are we talking about for negative vector? Negative vector are those ones that have the same magnitude but opposite direction. You notice I emphasize that opposite. What do we mean by opposite? Looking at here now, we have a representation of vector B, C, and D having the same magnitude. But if you take note, these two are the ones in opposite direction. This one is not in opposite direction, it's just on another direction on its own. So this one is going forward and this one is going backward. So we can say in such a case that B is a negative of D. So hope we can get that clearly now. So let us consider how we can use this to do some graphical representation of some little operations. Let's do an addition now. When you are asked to add two vectors together, what do? You take the bottom of one of them and you attach it to the head of the other. So let's say we are moving from an origin here and they tell you get A plus B. How can we do that? Now from this origin, what is A? A is 3 meters in this direction. So we go 3 meters. Do we get that? Now, we now take the bottom of the second one, which is B, and we attach it to it. So for B, this will be the origin, and it will move eastward 4 meters. Don't forget, we said we want to make sure we represent the lines very well. So this is A and this is B. So this will be the destination. So from here, if we move A to this side and we move B to this side, this will be our direction. So it will be like this. So this vector we have here would now be A plus B. Do we get that? So that is for addition. What about in the case of subtraction? In the case of subtraction, we just use this simple manipulation. If we have to do A minus B, for example, now, we just manipulate it and just represent this A minus B as A plus minus B. We know what minus B is when we talked about negative vectors. It is just going in the opposite direction. So let's represent this one now. Let's represent it here. So let's take this point as our origin. So for vector A, we move 3 meters in that direction, and from there now you go for the opposite direction of vector B. So instead of going from here to here for vector B, we are going to be going the other way. So instead of going towards this eastward, we are going to be going westward. So it is going to be coming back like this for us to have 4 meters. So this is the origin. So from the origin now to that point, so this will be vector A minus B. I hope we are able to get that clearly. So that will be the graphical representation of vector A minus B. So that's for addition and subtraction of 2 vectors on the graph. Now let's look at how to multiply a scalar quantity, that is a quantity without direction, with a vector. So we remember scalar quantities have only magnitude, they don't have direction. So scalar quantities are real numbers, they are just a quantity, they will just give you maybe 2, 4 or something like that. So let's say in the case of this A now, if we are told to multiply 2 and 2 and vector A, what do we do? When they say double of something, that means that thing plus itself. So this is the same thing as saying A plus A. So look at how the graph would be now. Let's say this is our origin. Going from this point, and we go 3 meters. So we add another one from this our new origin, and we go, and that is 3 meters. So this will be our destination. So looking at this, what will be the multiplication of this, the implication of this now? From origin to the end point now is going to be 6 meters in the direction of vector A. Do we take note of that? It is going to be 6 meters in the direction of vector A. So this, if we don't want to stress ourselves through the graphical method, is as good as saying when you multiply a vector with a scalar quantity, what you just do is multiply the coefficient of whatever is the whatever the magnitude of the vector is with the scalar quantity. So the direction remains the same. So that is that for that. Okay, so let's erase this from the board. Now let's consider some principles. In mathematics we call them laws that affects vector. There are some particular principles. If you are familiar with binary operation, you would know them. That is the cumulative law, the associative law, and the distributive law. What is the commutative law all about? The commutative law is all about telling you that if you have an expression, something operating on the other, it is commutative if you can just switch places. If you can just arrange it anyhow, how you wish to, and you will still get your answer the same, then it is commutative. So what we are saying for vector now is that if you have a vector A, remember we can represent our vector like this, and you add it to a vector B, for it to be commutative, which it is, then you should be able to rearrange this. You should be able to say, instead of putting B in front, I'll put B behind. So it will be B plus A. So simple. So this is what commutative law is talking about, that you can switch places. What about the associative? It's also talking about something like that. The associative law is talking about, it doesn't matter which brackets you open first. It doesn't matter which on which you operate first. Like for instance, if we have three vectors, A plus B plus C. If we have these three vectors, what it's simply telling us is that if you like, add A to B first. After that one, now add B. The addition that you get from this, now add it to C. And if you like, don't do it like that way. You can also do it this way. Add B to C first. When you add B to C, then you can now come back to A and add it together. Or you can also decide that you would add A and C first. When you are done adding it, then you will now come back and add it to B. So vectors are associative. So it doesn't matter which one you go for first. You will still get the same result. And the last one, the distributive law. That one is talking about the opening of brackets. So it says if you have a scalar quantity, just a scalar quantity, in this case, let's represent our scalar quantity by pi. Now, if you are opening an operation, A plus B, for vectors, you can do it the normal way you open your bracket. That is, this one times this one plus this one times this one. It should still be the same thing. So this one must give you so these are the three laws that affect vectors. So we are very sorry about the break in transmission there. We just lost transmission due to technical issues around there. So let's get back from